Okay, so in the last class, just before we end, we have started our discussion on this the different type of code conversion, right? For example, if you want to make a code conversion from this BCD uh, to XS3, right? So we are discussing, so we will not discuss it. We have discussed, how to do that and show like for any type of code conversion, what is the general process. So here we just see maybe for one of the example, and then we will skip this part. Okay. So here the input is BCD, right? So this is the input and output is the XS3, right? So in input is a BCD, right? BCD, like is like, for example, the equivalent of this zero is written by using 4 bits, right? 0000, like that 0001, like that up to 9 would be the valid BCD. So 9 stands for 0001, right? So these are the valid BCDs, right? And correspondingly, we have to create the XS3 output. XS3 means basically just adding 3 with this BCD number that will give you the XS3 code. So here, if we say that this input, these bits are A, B, C, D, and output is basically W, X, Y, Z. Then here for all these different inputs, we will have output. For example, for this output would be 0011. For this 0001, output would be 0100. For here 0010, this output would be 0101. Maybe I should be a bit careful while writing this because it should follow this. Otherwise, it would look ugly later on. Right, 0011. For this, it would be 0110. Right, 0100. It would be 0111. So you can check also in between. This is 4 equivalent, and this is 7, right? So it is fine. Then it is the correct conversion. Then 0101, it is 1000. Then 0110, right? For that it would be 0001. Then it will be 0111. It will be 1010. Then here it will be 11000, and here it will be 1011. This is 8, right? The other one is that 9. For 9 it is like this 100. So 9, and you can see this is 12. So this is the valid BCD, right? These are the like valid,
Sir,
right? Huh?
excuse me, sir. Sir,
Huh?
why can't the 10, 11 be the valid inputs? Or will they
Uh,
be considered as 1 and 1?
no, no, no. BCD means 4 bits, right? And it cannot be more than 9.
With 4 bits, we can represent up to 15 now.
Yes. So they are not the valid BCD because BCD is only valid from 0 to 9, means for these values only. So if we have like 0, suppose like 1010, which equivalent to 10, this is not a valid BCD because this has contained 4 bits, right? And 4 bits means one BCD, one BCD number, and this corresponds to 10, which is not valid in BCD because it is basically a decimal representation. And okay, decimal representation only, right? And decimal valid number is only from 0 to 9.
Okay, sir. Since we are writing for decimals, decimal digits, we will consider only 0 to 9.
0 to 9. And then like you could also have after that, but these are the like not valid, right? It is like 0010, like, right? We are not writing for all, and then 0111, right? These are not valid. And we will make sure while designing that at this input side, this ABCD value cannot be this like from here to here. These are not valid, right? So ABCD cannot have these values. Okay, so if we have, so if we can, if we can make sure that ABCD never takes these values, right? Then we can say, right, we do not care about what will be the output because we are sure that at the input side this can never happen, right? So we will represent them by using this cross, and this cross denotes the don't care, combinations. So this don't care combination means you can consider them as like as one if required, and if required, you can also consider them as zeros. Why considering zeros is also important? Because sometimes you have to also make from the truth table or from the K map what is the inverse function of a particular, right? Like suppose if you take all the ones, and make a group of them, what you will get? You will get the minimized version of that particular function. But if you combine all the zeros and try to derive the minimized output, that will give you the a bar, right? The inverse of that function. So it is important to consider that. So this cross indicates it might be 0, it might be 1. It does not matter for this particular case. So it will help us in minimizing our particular circuit. So for example, what next? Now see, these are the outputs, right? This W, this W, X, Y, Z, right? So output has 4 till this bit second, right? So we can consider these individual bits like W, X, Y, and Z, and see what will be the minimized output from that. So for that, what we have to do, we have to do a K map for like each 4 of them. Sorry, for each 4 of them. So here inputs are A, B, it is C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and just put the values here. Okay, so you can see here it is like starting with, so we're considering this W. Let me put it in this way. So now we are considering this W. So first one is 0, right? Second one is also 0. Third one is also 0. Fourth one, first, second, third, fourth one is also close 0. Fifth one, that is 1, 0, 0. Fifth one is also 0. Sixth one is 1. Then we have 1. Then also we have 1, right? Then what else? Where should be 1?
The bottom left.
Bottom left. Okay. Any more?
Yes, sir. And the next one.
And the next one. Okay. And where do we have the remaining? All 6 would be the cross, right? Don't care combinations. Right. Now you have to make a group. Okay. So how can you group?
So the lower half.
Lower half. Okay. So are you trying to say like we can group it like this?
Yes, sir.
Okay. So then W can be written as this or for all 4. So what will be the minimized expression for W for all this for this particular group?
A.
Sir, A.
A, right? Yeah, because you can see C and D, it's just like offering for all C and D values. So C and D will not be there. And for B also, it is changing from both for 1 and 0. So B will not be also there. So only A will be there. Okay. Okay. Can we make any other group here? Because we can see 3 ones has been left till now, right? So can you make a group?
Yes, sir. We can make
We
one
can
group.
make a group of 4.
Right. So these 4 we can make a group. Right? What will be the minimized term for this?
BD.
BD.
B, D. Okay. Any other group that we can make?
Yes, sir. We can make another
Again, a
group of
group of
4.
And what will be the
BC.
right? So if you have to make a circuit for W, then what will be there? So it is basically BD, right? You take BD, this is the output. You take BC, right? And you have A. Take an OR gate. This is so. If you have these bits as an input, right, and if you connect them in this fashion, that will produce the output. And this W is the one of the bit in the output. That means W will give you one of the bit for this XS3 code, right? Similarly, you can take now this X, right, and draw the Carnot map, find the minimized expression for X, and find the equivalent circuit of X. Same thing for Y, same thing for Z. So like that, if you know the truth table, for the input side to output side, now you should be able to implement like any type of converter. Fine. Is this what clear to you?
Yes, sir.
Okay. Great. So then I'm not doing it for this X, Y, Z. Okay. So you can just do it. It will be the same process. Okay. So next one is the uh, parity generator and parity checker circuit. So parity generator and parity checker circuit. So what do you mean by this parity? Okay. So before going to that, suppose let us consider we have an like here this is the sender and you are sending something, suppose some like digital code. Okay, say this 1010. Okay, this 4 bits you are sending as a package, and it has been transmitted. This is the receiver. This is the antennas actually, and at this receiving section they have received it, right? So this is the sender and this is receiver, right? So the sender knows that I have sent this, but from the receiver point of view, okay, suppose they receive like this 0011, right? So sender have sent like how much? It is 8 into 10, but receiver has received 11 equivalent, right? So which is not correct, but there is no way for the receiver to know what is the correct means what was the correct information, whether this information is correct or not, right, to check it or to confirm it. So for that purpose, one of the technique, very simple technique which is not been used now, it is quite it is not also that way a fruitful technique. So one of the technique is called to add one parity bit with this. For example, you like if I have to send this 1010, right? And if I am using odd parity, okay, if I am using odd parity, so that means I will see how many ones are there in this code. So there are two ones, right? Which is an even number. But then I will add addition or an extra one, okay, with this to make the total number, I mean, to make sure that the total number of ones in this signal is or in this information is odd, right? And I will also beforehand tell the receiver that I will be sending using the odd parity. So when sender will receive that, so suppose this first 4 bit has now changed to this one, right? And say this one is as intact, right? Then what the sender is expected to receive? Sender will receive this along with this one, right? Now this receiver will see that how many ones are there? 1, 2, 3, 4, right? So the number of ones are even. here, which is not odd, because the receiver prior to sender has already informed the receiver that I will be sending using the odd parity. So that means it is expected that in the received information the total number of ones would be odd. But here what receiver can see here, the of total number of ones are actually even. So sender will understand that this is not a correct information what I have received. So it will simply discard this information, and maybe if there is any request path, then the receiver can request the sender to send this particular data once again. Right. So this parity generator means parity generator would be there in this sender side. Okay. So before sending this information, there will be one circuit which is called parity generator, and that will generate this one. Okay. And suppose this information was not this. Okay. Suppose the information was this one, 1011 initially, right? Then this when this information has been passed through this odd parity generator, then it will see that total number of ones here are already odd, so it will add on 0 here. Okay, because it will make sure that the total number of ones in this signal, that what this has been sent, is odd, right? So here the information is the containing in the first 4 digits, and this 1 is the parity bit for the first case, and for the second case this is the information, and this is the parity bit. Okay, so this is the parity generator. So parity generator would be here from the sender side, whereas this in the receiver side it will be the parity checker circuit. Here it will check the parity, that whether the total number of ones that we are receiving is even or odd. Based on that, it will decide whether the information that we are receiving is correct or not. Right. So you understand, like this is one of the technique for checking that whether the received information is correct or not. But there are some issues. For example, suppose like what for this particular case, what we have said is that suppose this 110, right, and odd parity. So we are sending now this information, right, and at the receiving section, what we have received this. So from that you can detect the error detection. So can you detect the error here? Yes, because you can see here total number of ones are odd, and here total number of ones are even, right? So obviously you can detect the error, because but you do not know how to correct it, right? So you can only detect that there is some error, right? And you can see what was the error. Like if you see, if you like, if you are someone, okay, if you are someone, okay, who can actually like see both the sender side and the receiver side, then you know that this last bit got flipped, right? It become 0 to 1, and that has caused the error, right? And suppose in the next case the same thing, what the bit has been sent, and suppose the bit has been altered like that, 10 go then say 01. Okay, so once okay, say this one. Okay, so at the receiving side what we are getting is this one, right? Here see, two bits got flipped, right? One is this 0, right? This one got flipped to this one got flipped to like this 0, and the 0 got flipped to 1, right? But this one is as intact, right? So here parity checker circuit, while checking, it will check that total number of ones are actually odd, so it will consider it as an correct information that has been sent. But actually you can see, if you are someone who can see both, right, then you can clearly see actually this is not the correct information what has been received. So if two bits got flipped, right, then this particular circuit will not able to detect that error. Okay, if only odd number of ones are changing, then only this circuit can detect. So this is a limitation. Okay, prior to like we have seen this, we have not so far seen the circuit yet, but prior to that, like we know where is the circuit, the parity generator circuit, where is the parity checker circuit, and how does they work, and what is their limitation, right? So this is basically the limitation of this parity checker and parity, like this type of error checking technique, right? So now let us quickly do one example and see that how you can make this parity generator. Suppose the odd parity only we are considering, what will how the circuit will look like. Okay, say here we will consider and 3 bit 3 bit odd parity generator. So 3 bit means basically the information here would be containing of 3 bits. Okay, so the total information then that would be sent by the receiver would be 4 bits, because this is the information bit along with 1 bit for the parity, right? So what will be this message? The message will contain, if we say like the message is 3-bit XYZ, and what will be the output, means output of this parity generator. So there will be 4 bits, right? So 4 bits means, okay, let us not say it in this way, but let us here clearly write it that it is the parity bit, right? What will be the corresponding parity bit, and say the parity bit we are denoting by this symbol P, right? Then for this zero, all we have to write all possible combination for this input. Right, so these are all possible combinations input, right? Now can you please tell me what would be the corresponding parity bit for each case? For the first one, what will be?
1001.
1. Second?
0.
000.
Next?
Sir, that one is 1. That one is 1.
Okay, this will be 1. This one?
0.
This one?
1. 1. 0.
Right, okay, so these are the corresponding parity bit, right? Now how you will get the, then you have to generate this bit, right? So you have to generate this bit and you have to send this bit along with this message. So how do you, and you have to make a circuit to generate this parity bit. So how you will make it? No, I'm not asking about the circuit. I'm just asking like what is the process? How can you make it? Carnot map, right? Is it not clear to you?
Yes, sir.
Right. So X, Y, Z 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right. And here it is 1, then 0, then 0. Here it is 1, then here it is 0, 1, 1, 0. Isn't it? Okay. Yes, we have used Carnot map, but does it help?
No pair, sir.
No pair, right? So, but can you identify what will be the function?
Complement of XOR.
Only complements of XOR. So there are three things: X, Y, Z. So
Yes,
will
sir.
it be
Complement of X XOR Y XOR Z.
complement of X or Y or Z? Okay, I think this would come like this. Could you please check? Or you can actually interchange this. Could you please check? Are you getting this or not from this?
Sir, what is this dot sign representing?
This one? Which
Yes, sir.
one? This one? You tell. What is this symbol?
Sir, this is OR.
Hmm. Then what is this symbol? Forgot.
Sir, XNOR.
Uh, so I think we have done this. So let me just. See this? We have already done this. Isn't it?
Okay, sir. Yes, sir.
Huh. So have you checked? Are you getting
Yes,
like
sir.
from these values, right? And can you implement this circuit? It will be like simple, right? If you are considering this one, then first put an XOR between X and Y, then you stand exclusive NOR between this, and that will generate this parity bit, right? Okay. So this parity generator, I think, is pretty straightforward, right? Once you know the property, you should be able to design. I think design aspect is almost the similar, right? Now let us see what is the parity checker circuit. Parity checker. So again, we have 3 bits in the receiver side. I mean, from the sender side, 3 bits plus 1 bit for the as a parity. So it becomes total 4 bits, right? So here is basically the received signal, and there will be 4 bits X, Y, Z along with the parity bit, and we have to have a circuit which will say is this parity bit is correct or not correct, right? So we'll say that parity error. Okay, and we'll denote it as like say error, say E. Okay, if this error is been 1, then we'll consider that there is some error in the received signal. So there are 4 bits, so you have to write all 4 possible combinations, right? Starting from 0000 to 0001, 0010, 0011, 0100, 0101, 0110, 0111, then 1000, 1001. I think I will not write the remaining thing. I will not write the last, the combination. Okay. So these are the signal received, and this is the error bit. So now could you please tell me what would be the corresponding error? Will it be any error in the first received signal?
Yes,
Right?
sir.
Why? Because the sender has sent the odd parity, right? Sender is using the odd parity bit, right? So to remember that total number of ones that is that we will be receiving will be odd. So will there be any error in this first?
Yes, sir.
Okay. What about for the second one?
No, sir.
Third one also then 0. Fourth one, here total number of bits are like ones are even 2, so it will be 1. Here again it is like odd, only 1, so it is no error. Here only again even, so there is error. Here also even, there is error. Here no error. Here 0, no error. Here again even, so there is error. So like that, here all 4 ones, so here also error. So like that you have this parity, this parity error bit, right? Then what you have to do now, here this at the input side you have 4 bits. So now what you have to do, then you have to draw the Karnaugh map and see whether it is helpful in doing the minimization or not. So it is x, y, z, p, right? So again, write all the possible combinations, fill the kernel map, right? Fill the kernel map. For example, this is 1 0 0 1, then again 0 1 1 0. So the combination is coming something like that, right? Then it is 1 1 1 1. For here it will go. So here also this alternate things will come, right? So you can also see from here it is not that way helpful, this k map, okay, for doing the minimization. But what you get the idea is that what is the like is for this alternate position, the uh, what is expected, okay, for this type of. So do one thing, okay, please remember one thing. So what will be the equivalent functions if the ones are like this? It might be, right, also the kernel map might be something like this, okay, for 4 variable. Okay, so please check it out, okay, if the one might be like this also, na? That this, right, like that, the opposite to this, right? In that case, what will be the minimize function? Hmm? What will be the function, right? Right, previously we have seen, like, for this particular case, what will be the minimize function? That will save you some of your time. Otherwise, you have to like manipulate it, like. So here, but for this type of case, it will be either like XOR or XNOR. Okay, so that is almost you are sure. Right. So for this particular case, the function would be this error bit would be given as this x. Okay, by this. So then you can cross check it out. So if you have to make a then the circuit, it is again not pretty straightforward, right? Take this two, right? X, Y. This is Z. This is P, and then this will give you the error bit. So this is the simple parity checker circuit. This is called the 4-bit parity checker circuit. Okay, 4-bit parity checker. So when when people will say like there are 4-bit, but this is the 4-bit parity checker circuit. So that means you can from that, and you should also understand that the message contains of 3-bit. Right, you should always remember that, because 1 bit is for used for the parity. So the message that has been sent by the sender is of 3-bit, right? The last bit is not that way in providing any information other than means rather than providing only the whether there is any error or not. It is not providing any that way any other information. Is this parity checker circuit is yes.
Sir, how are we arriving to this error expression from the kernel map, or it is just by manual checking we can
It is actually, you can check it, you can you can actually do this type of thing, right? X dot y, put them and put the bits in the kernel map and see where what is their combination, like that only.
Okay, sir.
Okay, but if this type of alternate things are coming, right, this type of thing, then mostly just try to check with either XOR or XNOR.
Okay, sir.
Okay.
Sir,
Huh.
sir, is there a way to check if the bit positions are altered?
No, not with this one. Yeah, there are techniques, but that are a bit more complicated and not in our syllabus. Yeah, but there are techniques by which you can also point out if like which bit has been changed.
Okay, sir.
Right. Next one that we will do here is the magnitude comparator. So, from the name itself, it is clear like what this circuit will do. It basically will compare the magnitude of two numbers, right? And compare whether two binary numbers, right? Whether these two binary, which one is higher, which one is small, means which one is larger, which one is smaller. This, for example, let's say there are this two numbers, like binary numbers A and B, and each contains 4 bits. Okay, so it is A3, A2, A1, A0. Okay, this B3, B2, B1 and B0, right? So from here, if this number is like this, so for example, this number might be say 0101. Okay, and this number might be say 0111. Okay, this number, say any number can take any value, either 0 or 1. But the thing is that as they are like binary numbers, so this A0 or B0 or A1 or B1, like any of the single bit can take only either 0 or 1. It cannot take any other value, right? It should be within 0 or 1, binary, right? So here, first thing, if you are okay, if you try to think, manually, okay, even if you are trying, okay, means what you can do, you can, convert this one to in decimal, in if you are doing it manually, and you will find, right, this is for equivalent to 5, this is equivalent to 6, and 5 is smaller than 6, so this number is larger than this, right? That is one way. Right. But if you are not sure, okay, how to do that, okay, if you do not know how to convert it to the decimal one, then probably the other way would be first check the MSB. MSB is the most significant bit. That means the leftmost bit, right, which has the highest value in that, right? Because in digital you have seen, right? This is the 2 to the power 0. This is 2 to the power. This position has 2 to the power 1. This is 2 to the power 2. Then this position has 2 to the power 3. Right? If there is 1, then we have to make 1 into 2 to the power 3. So this is called the MSB, right? Like most significant digit. Similarly, the last one is called this LSB, right? Is the least significant bit, right? This one. So first start with this MSB and see, compare this number. Okay. So for example, here you can clearly see this the first two bits are 00, right? So if they are like 00, then no issue. No issue means in the sense then these bits are same, right? Then you cannot say which one either which whether A is higher or B is higher, right? Then you have to move the comparator or check for the second bit. So in the second bit, you see it is also 1 1. Again, they are same, right? So you cannot say still. Then move to the third bit, right? So here this third one is 0 and 1. Among 0 and 1, this 1 is larger, right? So definitely we can say B will be higher than A. So no need to even check for the fourth bit, right? Similarly, if you had suppose this number, okay, say 0 0 0 1, and here it is 0 1 1 1. Okay, for this, right, here while you are checking that the first MSB, so here itself you can tell it is 1, it is 0, right? So this A is higher, so for this case A is greater than B, right? And for this previous case, this B was greater than A, right? So here by checking this first bit only, you can tell like this is given, like this A is greater than B. So no need to think for the rest of the bits, right? Okay. Now the thing is that how you will understand, right, whether these two bits are same or not in a digital circuit. Give me any logic operation which will tell you two bits are same.
XNOR.
X
X
naught,
naught.
very X naught, very good. So because X naught, okay, what is the truth table of for X naught? If say this X, Y, and this F is the output. Please give me this
1001
one
001.
1001.
1001. So that means 1 0 0 1. So that means when these bits are different, right? So then this output are 0. When the bits are equal, for example, for these two, right, x and y, the output is 1, right? So that means if I take this x NOR gate and give here A3 and B3, right? And if this output is equal to 1, then I can say A3 equal to B3. Is this like, can I write it always?
Yes, sir.
Okay, so that way by using this gate, you can write whether one of the gate is higher or means like which bit is higher. Means not higher, means whether the bits are same or not, right? Okay. Now tell me, uh, so similarly for this particular case, first one is same, second one is same, so second one also you can use this XOR gate, right? So you can use this type of this thing. Here it is A2, here it is B2, right? So for this case, here also this is F is equal to 1, so A2 will be equal to B2. So here also the second bit is same. So what about then the third bit? Then you have to go to the third bit, right? But here third bit we can see B is greater than A. So tell me some logic operation that will give you this type of thing, like which bit is means some one bit is greater than the other bit.
B1 and complement of A1.
D1, very good. So D, you were saying B1, right? B1 and complement of A1. Please check. Have you said this? What
Yes,
am I
sir.
writing? Okay. So for here, what it does, if this B is equal to 1, A bar is an A1, suppose this is 1, and A1 is 0, and then A1 bar would be equal to like 1, then here it is 1, right? When this is 1, 1, the output will become also 1, right? So if this see here, this, okay, is it the correct or proper way to justify, or should I shift this here and then tell? Okay, just a minute. Right. So now we are considering about this greater operation, right? So here you can see this B1, if this B1 is 1 and this A bar is okay. So here this B1 is equal to 1 and A bar is A1 is equal to 0, right? And for this combination only, this output would be equal to 1. So if this output of this is equal to 1, then definitely we can say that here B1 is greater than A1, right? But this is for this is true for this particular these two number, right? Right. But it can happen that A1 is greater than B1. Can it not happen? Hello.
No, sir.
Why?
Sir, because if this happens, then B1 must be 0.
No. I am saying for this condition, when for this number, okay, this circuit will give you that 1, right? That is fine. But we might have some number like this, na? 1 1 say, then this 1 1 say, or this 0 0 here, say 1 0 1. So here if you consider, here this A1 is equal to 1 and B1 is equal to 0, right? So
Yes,
here
sir. Yes, sir.
definitely A1 is greater than B1, no? Right? So how do you check this?
AB bar.
A A1
A
B
and
bar,
B bar.
right?
Yes.
A1 B bar. Okay. And how we will get it? A1 B1 bar, right? So here, if you just think about these two, that for each bit, we have to compare for three cases, right? Whether these two bits are equal, whether that means whether A is equal to B, this is one criteria. Whether B is greater than A, this is the other criteria. The third criteria is whether A is greater than B, right? So for A is greater than B, you have to use this one, right? A1, B1 bar. Now, what I am trying to say from here is that this is which gate?
X not.
X NOT gate. This is which gate?
And
And this is also AND, right? So except this MSB, for each and every, or even for this, suppose if for MSB also, for like for each bit, okay, say in general, for each bit we have to check for three conditions: whether these two numbers are equal, whether one is greater than the other one. So there will be like three conditions. So for three cases, let's say this AN BN. Okay, what we have to do? How many gates we have to do, or I have to how many gates we have to use? That's what we are trying to analyze. So the first one is this one, A3 B3. This is XOR, XNOR, that will or say in general A and B, right? That will give me that A is equal to, if this is 1, if this flag become 1, then this A is equal to B, right? Or this A1 B A B1 A B bar, if this is 1, then that will give A greater than B. If the other one, if this is greater, if this is 1, then that means A is less than B, right? Okay. Now here what I'm trying to say is that while implementing this XNOR, okay, we can actually also get these functions, this A B bar and A bar B. Okay. What I'm trying to say is that if you want to implement this, right? So while you are trying to implement this, you will also get this. How? Just let me give you one example. Say from this A and B, what you can do is that you can take directly A. So that will give you here A bar. Yeah. So could you please check what is this function?
So A equal to B.
Huh?
XNOR.
No, here you cannot write A equal to B, right? This means I'm saying like express this F in terms of A and B.
So A bar B plus AB bar whole bar.
Right? So here it becomes A bar B, and here it becomes A B bar, right? Then we have an XNOR. So it is A bar B E plus A B bar whole bar, right? So can you minimize it? A bar B here this will now become dot, right?
Sir, it will be XNOR.
It will be XNOR, right? So again, A dot A bar, B dot B bar, plus you have A bar B bar plus AB. So this is 0, this is 0. So it becomes, so this function is actually this, right? So basically, if instead of using this X naught, if you are implementing the circuit like this, then in that process, what you are getting is that you are also getting this function and this function. Means you are also getting this one and this one. That means you are also, if you are implementing this like this, okay, then you are getting all three options. All three options means you are getting A equal to B if this flag is 1. You are getting B greater than A if this is 1. If this is 1, you are getting A greater than B, right? So for each bit, you can do like this and get like all three, you can actually compare, all these two bits, right? And you will get all these combinations from this only, right? Is this part clear to you?
Sir?
Hmm.
Sir, from the circuit, how we extract this A bar B line?
How you will extract this A bar B bar? Means I don't understand. What do you mean by A bar B bar?
Sir, I mean, we have made this circuit for checking whether A is equal to B or not.
Uh-huh.
But we also know that one of the lines also tells that whether A is greater than B or A is less than B.
Right.
Sir, so how we extract that data from this?
Means you are saying this data corresponding
sir.
to this? Okay.
Yes, sir.
Good question. So that we will take, in the next page, okay, where we will compare these 4 bits that we have started our discussions. So now we are comparing this A3, A2, A1, A0, and B3, B2 of B2, B1, B0, right? Now we have to compare, right? So when you are comparing, you have to take like bit by bit. So let us take first this A3, for this A3 and B3, right? So for this A3, B3, we will implement this one, right? This circuit, because this circuit will tell whether A3 equal to B3 or A3 greater than B3 or B3 greater than A3. All three it will tell us, 3 options, right? So for that, what we will do, here we will write A3, and then we have an AND gate. Here also we have an AND gate. Here we have this B3 followed by a NOT gate. Here we have connected this, and here we have connected this, right? So this is A3 bar B3. And here it is A3 B3 bar. Then we will use one, which gate we will use on NOR gate. So that will give us A3 B3, right? So this is for this A3 B3 one, huh? Right. So like that we have to do for other 3 bits. Yes, probably I need some space here, and I don't want to draw this circuit again and again. So what I will do, I'll copy it and paste it 4 times. Though I have to actually change the names. Yeah, maybe a little bit of space I have to give. Otherwise, Right. So here what I have done, I have pasted this four things here, right? And here definitely this thing will not be like A3, B3, but rather it would be A2, right? Like that. This will change now. So here, now it will become A2, B2, A1, B1, A0, B0, this not 1 1 1 1 1 1 2 2 2 2 2 2, right? Okay, now see how to do the final thing.
So
Okay,
one connection is missing in the
which connect? Yeah, oh, this copied. This thing has not been copied. Huh? Okay, right.
yes, sir.
Yes, thank you for pointing this out. Right. Ah, this is not the correct way to do that. Right. Okay. Right. So first we have to see for which conditions this number A will be equal to B. Okay. For which condition A will be equal to B?
All four bits are equal.
All four bits are equal. All four bits are equal means all four this has to be equal to 1. Am I right?
Yes, sir.
All four this output has to be equal to 1, right? All of them. So what we can do, we can take an AND gate, and that will be 4 input AND gate. We are considering the 4 input AND gate is available with us. So here we will take this. Then with this, I think the next one would be really tricky for me to draw. Yeah, because it might touch this one. But this is, you have understood, right? What I am trying to do, right? So all 4 bits will pass through this AND gate, and that function will give you, if this is equal to 1, this AND output of this AND gate is equal to 1, that is basically signifying this A is equal to B. Is that clear to you?
Yes, sir.
Okay, so let us then go to the next one. So when we can say A is less than B, when we can say A is less than B?
Taking the R over A3B,
Uh-huh.
A3 bar B3. Taking the R gate over the first term.
Taking the
R gate.
OR gate.
OR.
OR gate between whom?
Between A3 bar B3, A2 bar B2, A1 bar B1.
A3 between this one,
Between all first inputs.
all first, right? Between all. So will it be OR gate? Only OR gate will be sufficient. ORing of this would be sufficient.
Sir, shouldn't it be like we need to check A3 bar B3,
Ah,
then we need to check?
exactly. So you cannot actually do only OR operation between these 4, right? Because if you do OR operation between these 4, then see, okay, maybe one example, say you are doing A2, right? Say 0 1, then A is less than, right? 0 1, then say 1 1, and then say 0 0. Okay, so here we are comparing now whether A is greater than B to or not, right? So for this, what you will get, I think this is not a correct the correct one. Let me just change it a little bit. See here, if you are now comparing this one, eventually this is also not the correct one. Okay, let us consider these two bits, like A is this one and B is this one, right? So if you compare now B2, it seems this A is less than B, right? If you are doing the OR operation, if you do an OR operation between these two, right, that will not give you like something wrong, right? Here also they are equal, but if you do it for here, it will give an impression that only OR operation, that A is less than B, which is not correct, right? You can clearly see here actually A is greater than B. So only OR operation is not sufficient here. But
Sir, A
rather
is
what you
less
have,
than B, right?
huh?
A is less than B, right?
Oh, for this case, A is less than B, right? Right, you are right. Then let me change it. Right. Okay. So here, if you are comparing this second term, right, it gives an impression. Oh, again A is less than B, right? No. Then I have to just alter altogether. Okay. Right. So here, if you are comparing this second bit, then that gives an impression that A is less than B, but actually A is greater than B. Right. So, what do you think? How we should proceed?
Sir, we first check A3 and B3,
Hmm.
and then if it is equal, then we proceed to A2 and B2 and so on.
Right, right. So first we have to check whether A3 is equal to B3 or not, right? Okay. So for that we have to take this one. We have to take this one, right? A3, B3. Okay. So with this, what we have to check? Yeah, please tell me.
A2 is A2 is less than B2.
A2 less than B2, that means this, right?
Yes, sir.
This. So if both of them are on, means A3, B3 means, that means the A3, B3 are same. Then we have to come to A2 like B2, and this will give us this information whether A2 is less than B2 or not, right? You do an AND operation, right? That will basically tell us whether A2 is greater than, sorry, greater than or less than, which one? Less than, right? A2 is get less than B2 or not. Then what next?
We need to take
Sir, then we
A3.
can A2,
Then,
B2. No.
right. Then again, see, again you have to take this, right? I'm doing something. Please check whether you also agree with me or not.
Yes, sir.
Have I done correctly? So this if this output is 1, so that means A3 equal to B3, A2 equal to B2, but B1 is greater than A1. Is this correct? No one is saying anything.
Yes, sir. Yes, sir.
Yes, sir.
Okay. Okay. So the other one, okay, if I suppose take this, which is basically A3, B3 equal, then if I take this, which is basically A2, B2 equal, and then I take this, which gives A1 and B1, both of them are equal, and then take with AND operation this, then here this will give you this information. Isn't it? Isn't it correct?
Yes, sir.
Okay. So now we have got these three informations, Okay. Now, but then how to assure, or what should be the condition for A really less than B?
We take the OR of these three along with A3
Along with
A3 less than B3.
this, right? Along with this. So now what we will do? We will take an OR operation. Very good. We will take an OR operation between this, between this, between this, as well as this. So that will give us this information. A really less than B. Please check it out whether this circuit will work correctly for all different combinations or not.
Sir,
Hmm.
sir, why have you taken this A3 complement B3 in this OR gate?
Which OR gate?
Sir,
This OR gate,
yes, sir. Yes, sir.
last OR gate, A3 complement B3, because
Yes.
it might possible, right? That suppose like the numbers are like this, no? 1001, and the second one is this, right? So in that case, like A2, A1, A0 will be equal to B2, B1, B0, right? These three are same, but this MSB are different, and from this, okay, so I should not say this one is 1 and 0 because I am considering A less than B. So it would be the first one is 0 and the second one is 1. Have you understood my point?
Yes,
No?
sir. Sir. Yes, sir.
You understood, right? Okay, so it is 1, it is 0, right? So this is possible, right? From seeing here only, you can tell like A3 means A is less than B, right? Okay, and here please notice one more thing, that is these output. Okay, these output signifies that A3 equal to B3. This condition has been verified, and then we are checking A2 less than B2. Similarly, this operation, for this we have checked A2 equal to B2. We have checked A2 equal to A2 equal, sorry, A3 equal to B3. We have checked A2 equal to B2. Then we have checked for A1 less than B1. For this, we have checked A3 equal to B3. We have checked A2 equal to B2. We have checked A1 equal to B1. Then only we are checking A0 equal to, sorry, got up. Then only we are checking this A0 is less than this B0, right? So first three condition has been checked. Then only we are checking whether this comparison is valid or not. We are not doing only this, right? After doing all these things, only we are checking this. So basically that means we are doing an AND operation, right? So with all these things, if this is true, then only we can say, right, this number A is less than B. Okay, so this is all about A less than B, but we have left out with one more condition, which is A greater than B. So please tell me, how should we approach to find A greater than B?
So NOR of A equal to
Not
B
of
and A
A
less
equal
than
to
B.
B and
Not of?
So
A equal to
NOR,
B and A less than B. If both are 0, then we get 1. Then we get A greater than B.
Ha ha ha. So I'm saying from this circuit now. So here we have everything, right? Everything required, right? So how should we proceed now? First thing is that if this is one of the criteria, right? Right. So that means there will be another OR gate, which will say A greater than B, and for that we
Sir,
one of the
cannot we
output.
directly apply NAND gate across A equal to B and A less than B?
Uh-huh.
Cannot we directly apply NAND gate on A equal to B and A less than B?
Okay. Okay. You are saying like if these two conditions are not valid, then the third one is had to be valid, right?
Yes, sir.
Okay. I agree. Fine. Fine. But suppose in a particular circuit, you have to only find A, whether A greater than B or not. Okay. Then how you should approach? Similarly, right? How you have gone to, get this A greater than less than B, right? The same thing. So one output would come from here, right? Then for here you have to again have an second AND gate. So which will first check that whether this A3 B3 are equal, right? And then only you have to check this. Sorry. Then you have to only verify the second condition, that is this one, and like this, right? Like for this what we have done, and this will also go to here, right? Similarly, for here you should have one output from here, like which will say A3 equal to B3. Then you have to take this output which will say A2 equal to B2. Then you have to take this one which will say A is greater than means A1 is greater than B1, right? And then take also this output to this OR gate, right? Similarly, here you have to use one more OR gate, one more AND gate, where this is for A3 equal to B3, one input. Second check is for A2 equal to B2. Third check is for A1 equal to B1. Then fourth check is this A naught is greater than B naught. So here you can say A naught is greater than B naught, and then you can take this output from here. Then what you will get is A greater than B. Is this part clear to you?
Yes, sir.
Yes, sir.
Okay. Then let us move to the next one,
Sir,
which is
sir, will the circuits in the real life also this complex, like with these many things?
uh, see, this is like for a 4-bit comparator. 4-bit comparator is like this only. Okay. But the good thing about the circuit is that once you make, once you make it on the chip, okay, suppose, right, this is now this become 4-bit comparator. Okay, you have to make it only once, this block in your design, right? Then after that, if you need it, you just simply copy it and then paste it. Okay, so then you do not look what is inside this, because then it is almost type of ready-made block to you, available to you, right? But yes, this circuit is like this only. And if you suppose you have to implement this one in your laboratory with all these pins, you have to be very, very careful, right? Because there will be so many wires, right? I think other one you can also use. Yeah, just a minute. That, for if you can use this one, that is also fine. A3, B3, right? Then use and not get with this. That will this will give you A3, B3. So if you really want to minimize this circuit a little bit, right? Then right, or eventually if you can even make it a bit more simplified, A3 B3, and take A here, take B here, not get, and get the complements here only once. Okay, because this A bar B bar you will need for all, right, or for all bits, right? Then just for one case add this. This is A bar and this is B bar. In the other case, add this. like that. Okay. Yes, I think one of you were asking some question.
Sir, can we extend this idea from 4-bit to more than 4 bits?
Yes, but the circuit complexity will increase more,
Okay, sir.
isn't it? So see the logic is same, right? You have to like check individual bits. Then next one is called decoder. Okay, so decoder is something, say this is a decoder. Three to 8 line decoder. Okay, so that means here you have 3 lines, and in this output you have 1, 2, 3, 4, 5, 6, 7, 8, 8 lines. And these lines are being denoted as this D0, D1, D2, D3, D4, D5, D6, D7, right? All 8 lines. And here the inputs are, say, this X, Y, and Z. X, Y, and Z. So what decoder does is that you give any combination of X, Y, Z value, say like, any binary combination, obviously. So let's say like 1, 0, 0, say if you are giving 1, 0, 0, then what the decoder does, it will make sure that what is the value actually, decimal value equivalent to this?
4.
4. So what this decoder does, it will make sure that this D3 is on. So that will give output, send an output or make this D3 high. Means it will make D3 as 1. Other bits would be equal to 0. Right. Similarly, if you give suppose 1, 1, 1, right? So that will make this D7 to be 1, and remaining other bits would be equal to 0. Right. Similarly, if you give suppose 0, 0, 1, I should use some other color. If you give suppose 0, 0, 1, that will make this D1 to be equal to 1. So it is pretty
So
simple.
if you give 1 0 0, then will D3 or D4 become 1?
1, 0, 0, 1, 0, 0. Okay. You please tell me which one you think.
So D4 should be
Why?
high.
Why?
Sir, because
Please tell me because.
Yes, sir. D0 will give 0, D1 will give 1.
Because we have started here counting from 0, na? 0 to 7, right?
So D4 will be 1.
D4 will be 1. Will the D4 be on? Please check it out.
Yes.
Yes, sir.
yes, sir.
Okay. So please explain why.
Sir, both side the counting starts from 0.
Both side counting starts from 0. So, okay. Then let us, good that you have asked this. And then let us also write this input and output. So here input is X, Y, Z. Output is D0, D1, D2, D3, D4, D5, D6, D7. Okay, this is again the truth table. Okay, so we are doing the truth table so that, using this only we'll understand. If there is anything wrong, we'll definitely rectify it. So write all possible combinations. Okay. Okay. So when this XYZ is equal to 0, 0, 0, which bit do you think that will be high?
Sir, D0.
D0. D0 will be high. Remaining all bits would be equal to 0, all output. For this,
D1.
For this, D1 would be equal to 1 and all remaining bits would be equal to 0. For this, D2. For this, D3. For this, D4. For this, D5. For this, D6. For this, D7. Right? Okay. Now let us come back to the discussion that we are doing. So for 0, 0, 0, or no, 1, 0, 0, right? For 1, 0, 0, what should be the output? Now please check for 1, 0, 0. So for 1, 0, 0, what is the expected output?
D4.
D4. So this was wrong. Very good. You have pointed out and you have learned at the same time. Right? So for this, okay, I should have used this color. Right? Good. So you can see from here clearly. Then for 100, which is decimal equivalent is 4, so here it is D4. For 111, decimal equivalent is 7, so here it is D7. For 1001, decimal equivalent is 1, so you are getting D1. So whatever will be the decimal equivalent, you will directly get this. Okay. Now the thing is, can you implement this in a circuit? How do you implement? If I ask you to make a decoder circuit, this suppose 3 to 8 line decoder, can you make it quickly, please?
Sir, for every terminal, we can write the equations like
Right.
D0 will be X
Right,
bar,
right.
Y bar, Z
Yeah,
bar.
it is. See, it is very easy, right? So basically, D naught is what? See, D naught is basically it is X bar, Y bar, Z bar, isn't it? What is D1? D1 is equal to X bar, Y bar, Z. D2 is equal to X bar, Y, Z bar. D3 is equal to D4 is equal to D5 will be what? D6, D7, right? So you can easily make it. You take all this term, right? X, Y, Z, right? And get and AND gate. So for example, X bar, Y bar, Z bar, get and on gate, AND gate, and that will give you this D naught, right? Then you take the other one, X bar, Y bar, Z, then you will get D1. Right? Pretty simple. You need only this AND gate, and also you need some NOT gate to get this like inverse functions, right? So I hope this decoder circuit you can easily build. I am not doing the complete thing here because that will be pretty big in size, right? And this is nothing to do. It is pretty straightforward. Okay. Now, here is a question. If I ask you to design BCD you know that binary coded digit, BCD to decimal decoder. Please do it. BCD to decimal decoder. Or think how do you do it? So BCD is the input, right? And here is the output, right? Okay. BCD, how many bits? WXYZ, like 4 bits, right? Starting from 0000 to 0001, like dot. Then last will be 9, that is 1001, right? These are the valid BCD. After that, we also know there will be some other combinations, which is don't exist, right? So that means for the all the corresponding outputs, we can take as don't care combinations. But you have to make sure that this inputs will never arise at the input side. Okay, so now it is the decimal output. Okay, could you please tell me what should be the output here? Means how should I write the output here?
Sir, here also we will write the min terms.
So it will be D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, because it's decimal, right? It can only be the value from 0 to 9, right? Okay, so for the first one, 0, 0, 0, 0, this will be 1. Second one, this will be 1. For this last one here, this 9 will be 1, right? Then what? Then for this, okay, so for this here 1 and the remaining things will be here 0, 0 for these combinations, and here it will be cross, 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 means don't care combinations for this, right? For the don't care combinations, which is not valid BCD combinations. Then what you can do, then you can put a Karnaugh map, because now you have don't care combinations. So probably you can actually minimize this even more, right? So it is like A, B, C, not A, B, C, D. We are using W, X, Y, Z. So let us write that W, X, Y, Z. So it is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? Now for which combinations, like for 0, 0, 0, 0, here you are getting 1, and for so there will be how many don't care combinations?
6.
6. So I have drawn 4, means pointed out 4. So where the remaining 2 be, this would be there?
Bottom right
Bottom
and
right.
the left of it.
Right. But is this don't care combination is helpful for minimizing this function D0?
No, sir.
No.
No, sir.
No. So for this, probably for D0, it is not helpful. But for maybe if there is one right in the here, 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 or like any places right here, then it would be helpful. Then you can make out of 4, right? If right, or maybe 2 at least, you can make and minimize it, right? So here for D0, you can simply write this W bar, X bar, Y bar, Z bar. You cannot minimize it. Right? But if there is, suppose A1 is here, okay, suppose A1 is here, then you could have make a combination like this, or suppose if there is 1 on here, right, then you would have make a group of this. So like that you could have minimized it for a particular, like either, I don't know for which, this is which position actually, 0, 0, 0, 0, 0, 1. So for this last combination, right, this is the D7 combination. So for D7 combination, so D7 would be equal to, here it is W, and here it is Z, right? So D7 would be equal to W and Z.
Sir, it is 9, right?
It is 9, right? 9, right. It is 9
Yes,
only.
sir.
Right, right. I was thinking it is 7, right? It is 9, right? So D9 it will be WZ, right? Right. So you can
Sir,
actually get this idea, yeah.
what is the need of using a Karnaugh map? Means we know that corresponding to which expansion, binary expansion, we are getting which D value.
Right.
So
Okay.
like for
Suppose if you are not taking the K map, then from this, okay, what we could have written, D9 would be equal to these combinations, right? So D9 would be equal to W, X bar, Y bar, Z, right? We could have written this one, right? But if you are using Karnaugh map, then you are writing this WZ, right? So you can
yeah,
still minimize this.
Yes, sir.
Okay, but here it is important for doing this, making this don't care combinations, that this don't care combination should not arise, should not arise at this output ever. At this input side, it should not arise. You have to make sure that. Otherwise, right, like if this combination arise, then the corresponding output, like for this you will get some wrong output. Okay. Now, if I say implement this function f of x, y, z is so if I say now, so implement f of x, y, z means basically there are three variables, 1, 2, 4, and 7. You have to implement using a 3x8 decoder. So can you do it?
So we take the AND of 1, 2, 4, 7 and the knots from the others and take a total AND of them.
Okay. Okay. So here, okay, let us draw this 3 2x8 decoder as a black box. We are not drawing what is inside, right? But we know here there are three inputs, x, y, z, and the outputs are like 8, 3, 4, 5, 6, 7, 8. So it is D0, D1, D2, D3, D4, D5, D6, D7, right? Okay. So what is this D0 corresponds to? We have seen it here. So D0 corresponds to this, right?
Yes, sir.
Yes, sir.
Right? D1 corresponds to this. So this corresponds to x bar, y bar, z bar. D1 corresponds to x bar, y bar, z, right? So you can see actually this is what D0 is basically this, or okay, let's say D1. D1 is x bar, y bar, z. What is this one signify in this function?
X bar, Y bar,
X
Z.
bar, Y bar, Z.
X bar, y bar, z. So basically, if you represent them in a in this standard SOP sum of product form, then this number will actually point out this one only. Right. For example, here it is 1, so it is basically pointing out this D1. This is 2, basically it basically points out this D2. Right. It's basically 4. It points out this 4. It's 7. It points out this 7. So basically, this is D1. D1. D2 would be equal to what? This, right? This will be D2. D4 would be equal to this, and D7 would be equal to this, right? Now it has been asked to make this, right? So here these are the terms, right? So you know what are the terms. Then you have to make the get the this operation. So what you will do? You will take this D1, take this D2, take this D4, take this D7, and just connect them using an OR gate. Just connect them using an OR gate, right? And that will give you this function. Is that clear to you?
Yes, sir.
So then if any function is given to you, if you have a decoder, you should be able to implement it. Can we, okay, can we move forward?
So we have to connect D4. We have connected D5.
Oh, we have connected D5. Okay. Now it's okay, na? Is it okay now?
Yes, sir.
Okay. So there is one more thing which is called decoder with enable input. So this is basically what? This is basically a, suppose let us consider a 2x4 decoder. Two cross 4 decoder. So here there will be two inputs, say A and B, okay, as given in your book. Say A and B, and we have 4 outputs. So here we have an enable input. That means when this enable signal is available, okay, then only this decoder will change as this A and B changes. If this enable input is not available, then this decoder will not respond. Okay. For example, say, and for this enable will means enable will work when this enable is 0. So that means it is the inverse operation. Okay. So when the enable is 0, then only this decoder will work. Fine.
Sir, work in the sense will give correct output or will not give output?
Will give correct. Suppose you have given here 0, 1, right? And if this enable is 0 only, then only this D1 will be switched on. Means then the D1 will be high. Otherwise, D1 will be 0. So it is D0, D2, this is D3. And the truth table for correspondingly would be this enable input, input A, input B, and here outputs D0, D1, D2, D3, right? So here enable is 0, right? And then we have 0, 0. So AB 0, 0, then that means D1 will be high. Other things would be equal to 0. Enable 0, 0, 1, this will be high, other things would be 0. Enable 0, this would be 1, 0, 1, 0, then this would be high, other things would be 0. Enable 0, 1, 1. Fine. Now enable 1. Okay. Now whatever be the value, okay, whatever be the value of A and B, now enable this enable equal to 1 means basically it is disabled actually, right? Because we haven't bubble here. Bubble means it is this decoder will work only when the enable is equal to 0, right? So you can say like if this is 0, then only this 1 will transfer inside, right? You can think that way, right? So here for this case, it will have what will happen? It will produce 0, 0, 0, 0 for all these outputs, right? So this is the function of enable input. Okay. So what is the utility of this? Suppose you you do not want this decoder to be working, okay, until and unless a particular signal has arrived, then probably you can use some enable input here. Means this decoder should only work when some particular input has arrived, and the particular input has arrived when this enable in this enable terminal. Okay, so this is basically gives you additional one more advantage, that this will work only when you have provided this enable input. Otherwise, this decoder will not work. Right.
Sir,
Hmm.
how will we get to know that we have received the particular input or not using comparator?
No. Uh, uh, Actually, this is a part of a bigger circuit. Suppose you have suppose this is a decoder here, this block decoder. And here some inputs are coming, and here is this enable input, right? And before that, you have so many blocks, right? So here the inputs are coming, then from here these inputs are coming here, then from here inputs are coming here. Okay, so each and every step have some delay. Okay, so and suppose this is this output is fed to here, right? So if this enable you are not making here, if you are not disabling this decoder, then what will happen, right? Okay, let me put also here. Suppose this other input is coming through 2 blocks, and this input is coming through 3 blocks, right? So and say that there are equal, means there is equal delay, okay, for each block. So here the delay is 1, 2, 3 unit. Here the delay is 2 unit. Okay. So after 2 unit, this input has arrived. After 3 unit of delay, this input has arrived. Right. So this second input is arriving earlier than this input A. Right. So then if this is not enable input is not there, then whenever this B is arrived, this output will change. Then whenever this A arrived, output will change. And that might affect the next operation of these consecutive blocks, right? So for that, you can have a provision that this enable I will only I will only enable this decoder only when both the inputs, okay, here A and B, both the inputs are stable. Okay, then only I will enable this. Otherwise, until then, I will not enable it.
Okay, sir.
Okay, so this decoder with enable input can be used as a demultiplexer. Demultiplexer. So what is actually a multiplexing and what is demultiplexing is something like this. Say consider a block. Suppose here there are 4 inputs. Okay, this is multiplexer, right? Okay, so depending, and suppose you have only one channel. Okay, okay, and suppose these are the informations input, and you have to transfer this information to here. This is demultiplexer, right? And you have suppose only one channel here between here to here, right? So here you have given suppose 0 0, or you have given suppose one input here. Let us say this A input here. Here it is input B. Here it is input C, input D. Right, but you have only one channel, right? So what you can do, you can actually divide this total time slot, and first take the input from A, okay, then transfer it to here, then take the input from B, then transfer it to it, then take the input from C and transfer it to C here, then take the input from D, take it from this output here. So here the sequence would be like this. At first you are sending this A, okay, then you are sending B, then you are sending C, then you are sending D, right? But at the demultiplexer, there should be also some mechanism, right, by which this the exact information that has sent, and okay, by these inputs, that should be delivered to the desired output. Okay, so for that, when it receives this, suppose A, it has some mechanism by which this A will be delivered to this, A will be delivered to this, B will be delivered to this, okay, C will be delivered to this, and D will be delivered to this, right? So you have this multiplexer and demultiplexer, and so multiplexer means you have more number of channels at this input and you have less number of channel at this output, and you have some mechanism by which you will be able to transmit or send this this one of the input at a time. Okay, and demultiplexer is you have less number of input, more number of output. So depending upon what is the information, depending upon the here, there will be something called the selection line. Now you give the proper values of the selection line, and depending on that value, okay, the exact package will be delivered to the exact desired output. So this is the concept of this multiplexer, very simply. Okay, multiplexer and demultiplexer, right? Because this multiplexer also we have in our course, and we will learn it how to do that multiplexing. Okay, so here then first we are discussing with demultiplexer. Because why we are doing that? Because demultiplexer is nothing but we can, actually you can implement it using using this decoder with enable input. Right now we have finished this discussion, decoder with enable input. So I thought it would be easier for us to first learn about the demultiplexer. So here in demultiplexer, then in decoder, suppose 2x4 decoder. So what we have here, we have two input X and Y, right? We have an enable input, right? And we have four outputs, D0 to D3, right? So here these are inputs, this is enable, like that. Whereas for demultiplexer, we will use this enable and this inputs XY for some different other like some different way. Let's see that how we will do that. Here it is demultiplexer. Here we will take the input, this enable here. Okay, and we will take this enable as input. Take this XY line as selection line, right? And we have this D0, D1, D2, D3. So you understand, right? So here this inputs, we will take it as a selection line. Selection line means, because in decoder we know that if these values are 0, 0, then this line will be selected, right? If these values are 0, 1, then this line will be selected. So by using this, we are selecting which line means which line to be active, right? And what is the function of this enable here? Enable is, if this enable is fine, then only that output become high. So that means, in the other way, what we are using it here, if this enable is high, okay, if you are to correlate this, if this enable is high, okay, then and depending on the proper value of the selection line, that enable value should be transferred to that desired channel only. Right? If you change this value to say now 0, 1, now this enable value will be transferred to this D1, right? So that's why these lines are called the selection lines. This enable line, okay, this is called here the input line, okay, and these are the outputs as well, okay. So I hope you are able to correlate the decoder part and demultiplexer part.
Sir, here the enable will always be on, right? If it is
now here it depends how do you want to make it. Okay, you can make with enable 1, that means when this output is here, like, okay, what will be the desired output here? Suppose if all these D1, D0, D1, D2, D3 are initially 0, then if you give here enable 1, then you may change D1 to be equal to 1. You can design it that way, or you can design it other way also, that enable, it will be always in a one state. Whenever the data will come, then enable bit becomes 0, and then only the output will become equal to 1. So design it in your hand. How do you
Sir,
want to define?
if we design in such a way that enable equal to 1 will activate this demultiplexer, then we can select the output. If enable is 0, then all the outputs will be 0, right? So
Yeah, that's what I'm saying. Like it depends on the your truth table only, right? How you are going to define it. This is the truth table, right? It depends on how you are going to define your truth table. So depending on that, your design will change. Suppose here, instead of like this, I could have done it like this, right? Here, everything will become the only output, which is, suppose here D naught is 0, right? I could have designed it like this. You understand? Instead of, means which output is selected, the output becomes 0. The other output become 1. So they should always remain 1. Only the output which is on, that becomes 0. Have you understood this part, or you have still some confusion?
sir, I didn't get. I mean, if enable is always constant, then what is the necessary for connection between multiplexer and demultiplexer?
If enable is always constant, enable is not always constant. Whenever you are like for this particular design, when this enable is equal to 0, right, then only you can see like one of the output, okay, one of the output is 1, right? When the enable is equal to 1, then you see all the outputs are here 0. So it is not same. Is it same?
No, sir.
Yeah, then. So it depends on how you are designing, the circuit.
Okay, sir.
Okay. So,
So, but in the demultiplexer, the enable should be 1, and then we will get the output.
that I think you do it. You try to do it. Okay. So I'm giving you one example. I think today not much time is there, so you have to stop. So please do it like this. Say. Yeah, say this enable, whenever this enable equal to 0, okay, whenever this enable equal to 0, then only your output, like one of the output become equal to 1. Okay, one of the means enable will be 1 for all cases. Means if the data is not there, then enable equal to 1. If data is there, means the data is equal to 1, then the enable will become 0, the other way, and then one of the output will become equal to 1.
Sir, I didn't understand this thing. Means enable 1 means input is stable, right? For 2x4 decoder. Only then we
Enable?
will feed it. If enable is 1,
Hmm.
then we will consider that input as a correct input.
No, again that I'm saying that there is no hard and fast rule that the enable has to be 1, then only the input is correct input.
Okay, so
It
in
depends.
the previous table, you just switch. Means you are taking not of enable as stable
Right,
input, right?
right.
Okay.
It depends on how you are defining it. Okay.
Okay.
Let me ask, give you one truth table and then okay. Say this enable D0, D1, D2, D3. Okay. Say like yeah, for when these enables are this. Oh no. 0, 1, 0, 1, 0, 0, 1, 1. Okay. And here say this would be something like this. When this is 0, this would become 0. This become 1, this become 1, this become 1, and here this becomes 0, and here this become 1, this become 1, this becomes 0, this 1. This is for the fourth one, this is for the third one. Huh? For the fourth one, it become 1, 1, 1, 0. And when this enable is equal to 1, does not matter what is the value of this would become 0. Okay, so you have some decoder whose truth table is given in this way. So first thing would be implement the decoder circuit. Implement the decoder circuit. That is the first thing. Now, once you have implemented the decoder circuit, use that, then you have understood what is inside this. Then consider the decoder as a box. Okay, and consider this enable as an input and A and B as an selection line, and this 4 as the output, D0 to D1 as this output. Then whatever we have discussed so far from here, like if you have to go from decoder to demultiplexer, then maybe in the tomorrow's class, please tell me how means what is your design for this particular case, and if you are using this particular decoder as an demultiplexer, then what are the expected output, and for each input, like this for each selection value, for each different selection lines like 0 0 0 1, and for different values of E, what you were expecting at this output. Okay, so if you have any difficulty, we can continue from here in tomorrow's class. Okay, but I request you to please try this one by yourself at least once. Try this out. I think you will be able to understand like what I'm trying to say.
Got it, sir.
Hmm?
Understood, sir.
Okay.
So in the demultiplexer, since A, B, C, and D are all coming at the same one after the other, when Y gets a value, wouldn't X become 0?
X becomes 0. One thing. So here we are saying like A, B, C, D as input. Here we have written X, Y. So I think in your question you have used both A, B, C, D as well as X, Y.
No, sir. So I'm talking about the demultiplexer, sir.
Demultiplexer.
Yes, sir. So on the wire we pass A and then B and then C and then D, and then we get A, B, C, D separately.
Right.
So my question is, if supposing we feed this input into the demultiplexer from the selection line, so at any one point of time, will we only be able to get A or B or C or D?
Right. So it is basically called the time division multiplexing. So you give the user each time, say like first say okay, to make it very simple, say first 1 second for user A, first second 1 second, second 1 second. You give a time slot like 1 second for A, then the second like one more second for this B, third slot for C, fourth one for D, like that. Yeah, you are right. They will not get for continuously.
So when we're giving this as input to the demultiplexer, how do we separate the X and the Y, sir? So that is my question.
How do you separate X? Here there is no X and Y, na.
So
Here is A B C D, na.
So in the diagram below, you have drawn X and Y with an
Oh,
arrow.
X and Y as a selection line. Okay.
And so this is the selection line you said, right?
No. Here I was giving you. Yeah, I understood your point. Here I was giving you an example, which is of in real life, time division multiplexing scenario. Just to give an to make your to give an idea, how multiplexer and demultiplexer works together. Okay, please do not try to correlate this multiplexer, which is based on the time division, and with this. Okay, or if you want to correlate, maybe this is one of the way to correlate. Say for the first 1 second, okay, we know A has to be delivered here. Then what we will do, for the first 1 second, we will make sure the in selection line would be 0, 0. For the second, we will make sure the selection line is 0, 1. For the third second, it is 1, 0. For the fourth second, it is 1, 1. Right? That way you can deliver like this 1 to here, this to here. Is it?
Oh, so sir, the enabler is the input from which we're sending the
Right, exactly.
ABCD.
Exactly. That's what I said, na. So here actually this is basically the enable input. This one you are taking.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Okay, then thank you very much.
Upload these.
Sure. So thank you very much. So I think it's more than 10. Okay, so we'll meet tomorrow and discuss very much.
Sir, can you tell what is the syllabus of the next test?
Oh yeah, so the next test will be on next Wednesday, because Wednesday we have 2 hours class, and that will be from 8. So probably from 8 to 9 there will be written test. Means I'm just giving you some time. It may be 9 to 9, 5, 9, 10. Okay, the written test will be, the syllabus would be from MOSFET, op-amp, and digital. Okay, and then from 9:15 or 9:10, I mean, that depends, slightly. We will have an MCQ test. For that MCQ test, our syllabus, like as discussed, it will be the complete syllabus. And MCQ test will be conducted through Moodle. So we will only invest 1 day, that is the next Wednesday, and we will conduct both the test on the same day, so that you don't have to come again on the Thursday and give the exam.
So what will be the duration?
Duration for the written test will be, say, around 1 hour, and for the MCQ test maybe around 30 minutes, 35 minutes. I have not said the question yet, so it would be around that.
Okay, sir. Okay, sir. Thank you, sir.
Thank you, sir.
Okay, then. Thank you.
So,
Thank you.
so like
Thank
for
you,
the
sir.
compensatory test, like I asked you yesterday, you told that it would be like taken someday on the next week. So like, has a date been fixed for that?
Okay, so suppose, that's a good question. Actually, what if I for the compensatory test, if I take any day in the evenings?
So
Will it
like
be
it
fine?
would be easier if you could tell a like date in advance, because I'll have to prepare for other tests also during the
Okay,
exam.
understand. Okay, then what about the next Thursday during the our class hours, that is from 10 to 11?
So like, could it be taken on Saturday, like the 20th?
Please not drag it to that far, because after that we have to also check and all these things.
Actually, just Thursday I have an exam in the evening, so like if it could be held on Saturday,
Yeah.
it would be easier.
Okay, I
But
will
like
do
if
one thing.
that's not
I will,
possible,
let me do one thing. I will send an email, okay, to to all, okay, saying that those who have missed this test too, we are arranging a compensatory test, and I will propose the test as Thursday. Okay, so you please reply to that, and let me see what are the other replies that I am getting.
okay,
Okay,
sir.
if nobody is objecting for the Saturday, then I think it's fine.
Okay, sir.
Okay.
Yes.
Okay then.
Thank you, sir.
Thank you, sir.
Okay, thank you.